Okay, now when it comes to the heat capacity, we talk about that amount of heat absorbed by any object can actually result in some sort of temperature change, right? So that's the correlation between the heat energy and the temperature. Then we discussed that proportionality constant is generally called the heat capacity constant, which is depending on the mass of the object, which means it itself proportional to the mass. If I have a larger size object, you need the large amount of heat to change the 1 degree. But if I have a smaller size, same object, another object made of the same material, I need only small amount of heat, which means this constant is mass dependent. Because of that, we actually define the specific heat capacity constant, that is small c. So we usually use that constant when we do problems. Q is equal C times M delta T. So that C is specific heat capacity, which is equal Q divided by mass times the delta T. So I should be able to calculate this by using the concept of zeroth law of thermodynamics. That's the plan. So that zeroth law of thermodynamics is the one we're going to use for the calorimetry method. So the idea of the calorimetry method is very simple, which means we can heat an object, and then we can dump that object into another cold object, and then we can observe how the temperature change in the system. When the systems becomes come into some sort of steady state or the equilibrium state, then by using those information, mass of the objects, temperature, initial temperature, final of the objects, we can correlate those with the zeroth law of thermodynamics. Then we can build a small equation to find one variable. That's the plan. So that's what all we do with the calorimetry method. So to do that, I need to have a setup, which means that setup should not allow to any sort of heat exchange between the environment and the system. So the one assumption we're going to do this kind of calculation and also the experiment, heat exchange between the environment and the system is zero. Then only the zeroth law actually can be applied directly into there, okay? So what we do, we can take like a metal piece, for example, and then put it on top of a heater, like a hot plate, and then we can heat it. Let's say initial temperature is TH, that we can measure by using thermometer directly, right? So we can heat that into maybe 100 degrees C. That's what we do if it is in-person class. If this is in-person experiment, what we do, we're going to take a water beaker and then fill a little bit of water and then put the object inside and then heat this for like about until water boils properly. And then after the water boils, we're going to wait about like at least 5-10 minutes more. Then the idea is that then we can assume this whole object is at boiling temperature. So roughly about TH going to be something closer to 100 degrees C. If I keep enough time, the heat absorbed by the boiling water, then the object inside going to be reach that temperature. Okay. So we have to wait maybe at least 10 minutes to make sure the deep inside the object is at this temperature. If not, then that's going to be adding a lot of error into our final calculation. Okay. We are assuming the whole mass of the object, let's consider M, the total mass is actually at that temperature. Okay. But the simulator will simulate that nicely. So that one error, if it is an in-person experiment. Then what we do, we're going to put this into a colder system. So that system is our calorimetry, right? So what we do, we're going to take a smaller cup. We can make a calorimetry ourselves. If you have like a foam cup, the smaller one and the larger one, we can build a calorimeter. It's nothing else needed. What we're trying to do, we try to get rid of basically any sort of conduction, convection, and radiation from the system. We cannot avoid those fully. Like we will not be able to avoid those 100%. But if we can avoid them, get rid of those heat transfer mechanism at least 90%, 95%, 98%, that's good enough. So we will get a little bit of error anyway under this kind of settings in our experiment. But if you go into a research lab, then they have a special condition, specific setups actually to run this kind of experiment by cutting down those thermal mechanism almost very close to 100%, but not in our labs. Okay, so what we do, we have generally aluminium containers in the lab. So we're going to take a small aluminium container, and then that usually have a lid, plastic lid that has a two hole. One is actually for stir, other one is actually for the thermometer. So we use all the type thermometers, which actually, we have mercury little bit inside that. When the temperature absorb, the volume increases of the mercury. So that volume increases amount this kind of thermometers. Like here we have a liquid mercury. So that as the temperature absorb, that will expand the volume. So as a result of that, we will see this will rise on this like very small capillary line. So then that is actually calibrated with the degrees Celsius usually. And then we can read the temperature, that's it. If it is at room temperature, it will read the room temperature, usually about 25 C. And then as it is changing with the different environment right here, then I can read the capillary level is rising, then I can read the temperature carefully. But there's error associated with that again because these thermometers are not really good for this kind of experiment. If we can use like thermocouple, it's actually much better. But for this particular setup, in-person class, we don't have a thermocouple to use. So that's a little bit challenge, but usually we're getting fairly decent result. But the thermal expansion X setup, we have a thermocouple. So what thermocouple does, it can actually generate a small resistance difference. So it's just two wires. So each wire is actually sensitive to the resistance, temperature, resistance of the wire sensitive to the temperature, which means if I have a thermocouple at one temperature, I'm going to measure one particular resistor value. If I put the same thermocouple into a different temperature, the resistance of the thermocouple change. So what we're measuring is actually the resistance change. Then we have a table which calibrated that resistance change into the temperature. So we can use that calibrated table to figure out what is the temperature change. Usually that is very accurate. So, but it doesn't matter. We usually get a fairly decent answer with this one, but the simulator will give us really good result because it's too accurate. All right, so what we do, we're going to put the thermometer, and then thermometer will read the inner temperature. We're going to put about like some water here. Then we have a water mass of the calorimeter, like say MC. Then the heat capacity of the water we know is standard value, and the heat capacity of calorimeter also we know is standard value. Then what we do, we're going to put an outer container for this one, because we try to avoid as much as thermal convection, thermal radiation, and thermal conduction. Then we're going to set up this like hanging on the inside the outer container. Inner container is actually our container with the water. Outer container is another usually large aluminium cylinder. So nothing there. So the inside this part right here is air. So we try to isolate out that inner part as much as we could. Then that's it. Then we need to do this measurement first. Okay, mass of the water, and we should know amount of mass of the calorimeter plus the stir. And then we're gonna heat this object and then put that into the container as quickly as possible. There should be enough gap between these two, at least about few feet. If I put these two very close to each other, then the heat can absorb. So that may not be a good idea. So we're going to keep like at least 3 feet separation, 3 to 4 feet separation. And when I try to transfer that again, there's another error, because as far as I bring in the object from here to here, object is on outside here. So they're actually losing the amount of heat. We can't do anything about it. We're going to lose a little bit, but we have to do that transfer quickly as possible within like few seconds. Like within like 5 seconds should be fine. Then that's it. After you put that object in, hot object goes in, and now it becomes a system. Now your system has a hot object losing the heat, and the colder 2 object, which actually calorimeter plus the water, which absorbing the heat. Now I can assume there's no heat lost to the environment. All the heat from the hot object directly going to absorb by the colder 2 objects, calorimeter plus the water. If I add all of those together, should give you 0. So that's the idea of conservation of energy there. Okay. And the zeroth law of thermodynamics. Zeroth law telling you hot object always transfer the heat towards the colder. And the conservation of energy tells us that if there's energy loss, this is actually losing amount of energy. This is actually absorbing amount of energy. Losing energy should be negative. Absorbing energy is positive. Then if you add them together, I should get 0. That's a conservation of energy. That's it. Then by using this equation, I can build an equation to figure out, for example, heat capacity of this metal piece, C. So we can write it down, heat absorb, this guy right here, heat loss from the hot object, mass of the hot object, heat capacity of the hot object, times the delta T gonna be heat final, temperature final minus the temperature initial, TH, okay? Delta T always final minus initial, okay? T final minus T initial. T final is the temperature we're detecting here. T initial is actually the hot object temperature right here. TH is larger. Because of that, this whole part is actually negative, okay? TH is larger than T final. And in this part, we can write for 2 types. One is mass of the water, specific heat of the water, T final minus T initial, which is a positive number. And also mass of the calorimeter, specific heat of the calorimeter, T final minus T initial. So we use that in class work actually to do at least a detailed problem there. So then that's it. Then I have equation, which is everything equal to 0. If I know all of these except this guy, then I can find it. That's it. This part is negative, other 2 part is positive. Then I should get at the end a positive number because heat capacity is just a number. Okay. All right, guys. Any question? Okay, then the simulator has a simulator makes this more easier because the simulator does not consider heat absorbed by the calorimeter. So which means the simulator will result automatically amount of heat lost by the hot object directly go into the amount of heat absorbed by the water inside the calorimeter. So that makes calculation much more easier than we usually do in real life scenario. Okay, so that makes it much more easier. So if we identify the object heat capacity, then by using that number, we can actually identify what is that material is, because specific heat capacity unique to the material or element or alloy. So we can actually identify what that material is to. Okay, that part of the game, if you do this in-person class. So you're going to be given like maybe a brass object, a copper object, or maybe a zinc object. We don't know which is which. We can identify with the colors a little bit. Copper is more yellowish color and then so on, but we don't know exactly. But after we do the calculation, we can actually really identify which object is which. Okay, that's planned, but the simulator will tell us all those information much easier. Then that's it. Then finally we'll do the latent heat. Latent heat of fusion means some sort of solid has to transfer into a liquid form. During that time, there should be some energy needed to break the solidity, internal atomic level, the microscopic level bonding nature of the material. That amount of heat absorbed for that purpose is actually not going to be affected into the temperature change. So that was the problem when the phase change is happening. So during that time, there should be amount of heat absorbed that equal mass times the some amount of uh, internal intrinsic property of the material, which we call the latent heat now. So that amount of latent heat I can find again. I cannot directly measure this, okay? I can't directly measure that, but I can find that if I can do a phase change. And also at the same time, if I can do an experiment by using the calorimeter, by using that concept, I can write an equation by combining the conservation of energy and the zero law of thermodynamics. That equation can be used to figure out the LA. That's the plan. So how to do that? We usually gonna get the ice pieces. Few of them may be like 20, 25 gram of our ice pieces. And then that ice pieces we can actually transfer into our calorimeter. So if I transfer the ice pieces into the calorimeter, what will happen? Initially, calorimeter has a temperature Ti, something close to room temperature 25 C. Ice is usually in 0 degrees C. So now after you put the ice in, ice will absorb the amount of heat. As a result of that, this TF gonna be less than Ti. It will slowly decrease from the room temperature. So I can detect these two temperatures. This is actually the T cold of the ice that we know. Then we can write again. We know now again the hot object now is the calorimeter plus the water. Now that sending the heat to the ice now. First ice should melt, which means the ice needed amount of heat to go from solid ice to the liquid zero ice, and that liquid zero ice should be transferred into the zero temperature to the final temperature. Usually that final temperature, if it is in-person work, only like few degrees different, maybe like we can put like 10 grams maybe into the 10 gram of ice, or maybe 20 gram of ice. Then the amount of temperature change we can achieve like 5 degree max. That's what we usually get, or maybe 3 degrees most of the time. We can't get more than that. But in the simulator, we can actually do it very nicely. We can put more ice in, and then temperature change can be like 10 degrees in this experiment. That little bit challenging experiment, the error is so high because of various reasons. One of the error attached with this one is when you bring the ice from the refrigerator and out, immediately ice is starting to melt. If you take a look, the ice piece, always there is a water layer around it. So when you transfer in the ice into the system, then into the calorimeter system, then that water layer also transferring, but we cannot do any calculation for that water layer. We don't know how much is there, and then we cannot actually do anything about it. So usually we take the papers, like the paper towels, before we transfer, we put the ice with the paper towel and then try to get rid of that water layer before we put it in. But it can't be avoided. It's one of the major error happening during that experiment. That actually the major error. That gives us fairly large error always usually. All right, so then we know I needed another amount of heat. That amount of, I'm going to put Mi for the ice mass, okay? Mi is the mass of the ice, and the Ci is actually the heat capacity of the water now, because amount of mass ice converted into the water 0 degree, and that gonna change into T final minus T initial. And that's it. T initial is actually for this case 0. Okay. So this part is 0. This one will be just Mi CW times the TF, and then other amount of heat we needed for the water and the calorimeter. So I have MW, CW, T final minus T initial. Now in this case, this part is a negative value because T final is actually lower than T initial, okay? These are positive values for this case. Those absorbing heat, this is actually losing heat. That the way I define might be different the way your chemistry professor defined that heat absorb and heat loss. You have to be very careful and very specific when we go into next two chapters, okay? Uh, because that the way I am defining the heat absorbing and heat loss is connected to the next two chapters very much. If you mix those up, then you will get completely wrong answer in next two chapters. We need to be very careful, okay? That's all based on how you write this formula. You can see I'm writing here more generally, go towards all the way to the physics one class, because that is a kind of energy equation. So which means if I have energy change, that should be equal to zero. So I'm not writing energy initial equal energy final. That's another way usually some writing. Delta E initial equal delta E final. That is not the way I'm writing, okay? I'm writing if I add these two together, then I must get zero, which means one should be positive, one should be negative always. Be careful with those things the way, and depending on the textbook you refer and then resources you're following, slightly going to be different, but at the end, all we should end up with the same answer. Okay, so that's the important part. That's it. Then again, we can say Q1 plus Q2 plus Q3 should result zero, because two of them are positive, one of them negative. If there's no energy loss, energy transfer between the system and environment, that must result zero. Then if I know all of these mass, all of these temperatures, then I can find the LF. That's the plan. I write here only the water. The reason the simulator actually doesn't care the calorimeter, okay, that metal part. So if it is in-person experiment, I have to have another part right here, Q4, which is actually for calorimeter metal. So the M of calorimeter, C of calorimeter, T final minus T initial, that also should be included. Okay, guys, so that's the last part. So any question? Okay, then let's continue. This is going to be a group report, right? According to our schedule. Right here, this is supposed to be a group report, which means we have like, we're going to try to do like 4 different type of items to figure out the specific heat capacity. We'll do 2 unknown metals and then 2 unknown liquids. Usually that liquid part we not doing in person setting, but with the simulator it is actually easy to do. We will do together one of these very in detail, all the calculation. And then I will put you into the breakout rooms. In the breakout rooms, you can complete together the other parts, okay? So that breakout rooms, people are going to be your group members. So you make sure you connect with them, talk to them. Some of you might be know, some of you don't know, but that's okay. Make sure that is your group members, okay? We can put like maybe 3-member group probably. That's the plan. But if you want to do individual reports, that's totally fine. You can do all 6 of them as individual report. Even you go into the breakout rooms, this Excel sheet you have to do alone. Doesn't matter how many people are in the group, every people must complete the Excel sheet. Every person must submit the Excel sheet to the Moodle, okay? When you're doing the group report, I need only one report per group, including that last page detailing which member did what, okay? All right, so yeah, we will go into the simulator in a bit. We'll do first one, this one together, then we can talk about that. Technically, it doesn't matter. You can pick any numbers. As far as we use in numbers here correctly, we will get the right answer. All right, for the simulator for this one on page number 3 on the very top, if you click on that link, that should open up this kind of page. That page is usually give you this kind of error if the size of the browser is not enough. Okay, you see it says please view this activity on the larger screen. The reason I actually have a smaller size now in my browser, if I expand that, it will automatically correct it. Okay, it's not an error or anything. That simulator runs when the size of the browser is larger. Then you can click the experiment, third option on the very top. There's 3 blue options, blue icons, and then you can click run experiment. Second blue icon on the middle, then you will get this picture. Now we're ready to do the experiment. It's fairly very simple now. That's a heater left-hand side, which I mentioned earlier, and that is a beaker. We usually use the same kind of setup. And then in the beaker, we can fill the little bit of water, put any object in, let boils the water, and then wait maybe like 10 minutes after the boiling is done. And then we can transfer the object into the calorimeter. Right-hand side is a calorimeter. It has a steer, thermometer attached, and this will show us a little bit more detail. Thermometer is a digital scale, and steer actually also electronic one. It will rotate automatically, but in the real in-person class, we don't have this kind of calorimeter. It's just 2 containers, aluminum containers, one larger, one small. Steer, you have to actually steer yourself, one person, and then one person have to look for the temperature in the thermometer and then get the right temperature after system reaches equilibrium or the steady state. So that's a little bit work we have to do there if it is in-person real experiment, but this will generate more easy result. It will give us a final answer very easily. Okay, guys, any question? Okay, then if you go into the very left-hand side selection tool, it's a liquid right here. Change that into solid because we're going to use a solid unknown material first. There's a lot of option here, right? Because this is made for actually chemistry class, this whole simulator. I'm using it, but it is actually made for chemistry. So we'll use 2 metals. We can pick maybe unknown metal 1. And the mass of the unknown metal, you can put the largest, about 50 gram. That's the amount of size of the metal we're using if it is in-person work. And then temperature, I can put it into 200. That's okay. If it in-person work, that will not be 200. That will be about something close to 100. That's the maximum we can get. Okay. And then if you click right here, it will tell you the specific heat of that item, which we actually using that about 300.388 joule per gram. Joule per kilogram, it's about like 388. Now, after you select all of those, there's a next icon on left-hand side, very bottom. You click that, then you can start do any changes to the calorimeter. Okay. Calorimeter need to have liquid. You can fill that with the water and we can apply the maximum amount of water possible, 200 grams. And water initial temperature, leave it 20. That's okay. We can change that into 25, but we'll start at 20, nothing much to worry. You can click the specific heat that will show us the specific heat of the water, 4.18 joule per gram, 4,184 joule per kilogram. Okay. Click the next again, left-hand side bottom corner. Now we're ready to start. Now, one thing I forgot to mention earlier, how to detect the steady state. That's very important. So after you transfer the object, hot object into the cold object, hot object will losing energy, cold object will absorbing the energy. So the simulator will show you how the temperature varies. That's why the simulator is really nice. as a function of time how the temperature varies for both objects. So technically hot object going to start at high temperature and then slowly decrease in the temperature, okay? And then colder object is starting at low temperature because our calorimeter is at about room temperature, and then absorbing the heat, temperature will increase slowly. Eventually, this will reach into a one single temperature. That's the steady state. That's actually the equilibrium state. Okay, so that is where we actually wanted to read the temperature. That will be the final temperature of the system, T final. Now that T final little bit tricky to get in the real life scenario. You're not going to see any of these things, and then we cannot make those graphs either. Impossible. So what we do usually, we're going to detect the temperature of this guy slowly. It's going to start from room temperature, usually as a function of time. Start at room temperature and then slowly starting to rise. And then eventually you will see that will become steady, will not change at all. That's the right temperature, final temperature we needed. Problem with the in-person experiment, if you wait too low or if you did not observe that like continuously, if you pass this time frame, about maybe a few minutes there, not more, then this temperature will starting to decrease. The reason there's actually the energy loss from the system. Okay, we cannot avoid it. As far as energy loss is there, this will go back again. That will not happen like very quickly. There's like enough time here, like 10 minutes or so. It will be at least 5 minutes. It will stay there. But if you're not careful enough, then we might lose that window. If we miss that window, then we cannot get the T final. That's one of the huge problem for in-person work, but that actually automatically simulated here. We don't need to worry about anything. We just click the start button, let it run, and then read this, right? So that much easier and very straightforward. Okay, guys, any question? That's it. You can click this show graph right here. You click if you want spectroscopically the atomic or the molecular vibration behave in the two system too. We don't care that much. And then all you have to do, click the start button, and that will put the object in. Hot object is here starting, temperature will changing, starting from 20, slowly increases. And then you can see hot object temperature decreases, colder object increases, and then eventually two lines becomes one line, and then steady horizontal line. Temperature doesn't change as a function of time. That's the steady point. So we need to read the temperature when it reaches there. So the simulator automatically stop when it reaches there. So the maximum temperature the system can reach is about 24.08. That's the point, critical point we need to read accurately in our real experiment. If you read before reaching that, we have a lot of error. If you wait too long, we're going to be missing that maximum point. So somebody has to continuously observe because we're using that thermometer too, because that also not super sensitive. All the type thermometers, you have to continuously look that level, the mercury level on the very top. That changes slowly, then we have to read as quickly as possible. All right, guys, so that's it. Then we'll write it down the data here. We can include the non-parameters also. You can see some of them actually can be considered as non-parameters. For example, specific heat of the object, that is C0. The given value is the number right here, 0.388. Unit is actually joule per gram per Celsius, okay? And then I can include the specific heat of the water. That is also given. Unit is 4.184. Again, joule per gram per Celsius. Okay, those are in a way given numbers, okay? And let's continue. Mass should be in, we'll use the mass in gram. It is not the SI unit. Why we're using it? Because you can see the numbers given here is standard values in terms of joule per gram. Because of that, our calculated value also will calculate a joule per gram. Then it is easy to compare. Okay, but the conversion is very simple. If you multiply denominator by 10 to the negative 3 goes to the numerator, all these numbers has to multiply by 10 to the positive 3 to get it into the kilogram. Okay. All right, so the initial mass of the object is about 50 grams. Use at least all the decimal places observable, which mean at least one decimal place for 50, okay? Should not have two. So we'll cut down one of them, home menu bar, numbers, and then you can use the two arrows to get rid of zeros or add zeros, okay? Right arrow getting rid of, left arrow adding the zeros. One decimal. And the initial temperature of the hot object 200, but we'll add 10 there because actual simulator can show us 4 sigfigs, okay? If you go to any other temperature, it will show us extra 1 decimal place. So we'll keep that 1 decimal place accuracy in unit Celsius. Okay, then mass of the water. Remember, the simulator doesn't have the metal part, right? Mass of the water again in grams, 200. We'll use 1 decimal place extra. Otherwise, accuracy wise, it may not be a good idea. And initial temperature of the water, 20 C in unit Celsius with 1 extra decimal place. And final temperature the system reaches, which is again in unit Celsius, 24.08. Okay. That has to have all the sigfigs what we can read, which means both decimal places. That's all the data actually. Even we're doing this experiment, only important data point is that final temperature. That's create a lot of error. We cannot read before it reaching the steady point. We cannot read after it passed the steady point either. So we have to carefully get that number. So that mistake usually sometimes can create a lot of error, 10%, 15% error. Okay, guys, so we'll take a screenshot of the simulator here. There's only one simulator we need for this experiment. So you need to get this whole part, okay? Everything. That is our simulator. Make sure picture size smaller in size, should not be larger than 1/4 of the page. Any of the simulator pictures should be smaller than 1/4. Size of the 1/4 of the page or smaller. If you have a simulator picture or any picture, make sure you name it as a figure. Usually figure name goes below, table name goes on the top of the table. Okay, that's the standard publication format in scientific publication, not the industrial publication or anything. Okay. Figure 1, we can say heat capacity simulator. You can name it your way. All right, then you can add that part, add this part, picture part into the procedure section, link of the simulator to the procedure section. Then you have to explain step by step how you collecting the data. Do not copy paste anything directly from the lab manual. Okay, lab manual has some step written here, but do not copy paste anything because if you do that, that will identify as a plagiarize, then you will get a huge point reduction. Okay, if you write in the group report, that way you have to be careful. You need to make sure everybody doing their part precisely. Because if somebody lazy, if that person doing this part, then he might copy paste everything. There are going to be a huge point reduction for that part that will affect to everyone in the group. I cannot do anything about it, okay? I'm not going to grade according to the person who did which part. I'm going to grade the whole lab. So you have to make sure communicate properly. If somebody doing not correct, the only thing you can do like kick that person from the group. Don't worry about that guy. Get rid of the name. Do everything yourself. Submit your report. That's it. We will give that person the 0. Okay, guys. Any question? All right. Then we'll take a look how to calculate our heat capacity. We know the formula. We just need to investigate that. So specific heat capacity expected or given value for unknown one, we know 0.388. We're going to use unit joule per gram per Celsius, and which is about 0.388. And let's calculate that with the same unit, joule per gram per Celsius. And that calculation, if you remember the formula, discussed that earlier. So now we're considering only these two parts, okay? So we'll build the equation for this part. So this goes to the other side. I need to keep the C part here. This is going to be minus MW CW T final minus T initial divide by mass of the object times the T final minus the TH. This part T final minus the TH is actually a negative number. This negative sign should cancel out. Okay, you can correct it if you want to. Before you type in the equation, I can write MW CW T final minus T initial divide by M times TH minus TA. Then you will get a positive number correctly. Be careful with that. This must be a positive number at the end. That is a specific heat capacity. Okay. All right. So let's write that function with the Excel. Make sure all the Excel function included under the table. Equal sign. I need parentheses there. Mass of the water, click on the cell E number 10, multiply by specific heat capacity of the water 4.184, and multiply by parentheses temperature different final minus initial G10 minus F10, close bracket again, divide by open bracket mass of the unknown metal, multiply by parentheses temperature different, usually T final minus T initial, but I get rid of the negative sign, which means I can write it down T hot minus T final, okay? And close bracket twice, then hit enter. This is a simulated result. We're getting very perfect answer. This is a calculated value. We'll add maybe like at least 1 decimal place more, then we can see slight difference, but the difference is just a rounding error. Okay, it's a simulated result. We're not going to get mostly the errors. Okay, so this is, we can say, specific heat capacity of unknown metal 1. All right, guys, so that's very simple. Then we'll compare these two. Equal parentheses ABS open brackets expected value minus calculated close bracket divide by open double bracket open bracket. We don't need actually bracket there. Just divide by the expected value close bracket multiply by 100. Very small. Make sure percentage error does not have many sig figs or anything, like visible at least one significant figure. That should be good enough. Because we're interested to see whether that's a large number or not. If it is a small number, we know these two are close to each other. If this is larger, we know there's error. That's it. All right, guys, question. Okay, so that's very simple. And then one more thing we can take a look for each case is actually how much heat absorbed and how much heat loss. We know generally zeroth law of thermodynamics should be valid. Amount of heat absorbed should be equal to the amount of heat loss. So if we calculate that too, I should get exactly same numbers. This is a simulated result. We will get really, really good numbers. But if it is an in-person class experiment, we will see a difference, okay? Because there's no way to get perfect result in real experiments, okay? We'll do that calculation also for case by case. We'll do it in units joule, and then we'll compare the heat absorbed and heat loss together. We should get percentage error 0 technically. So we'll do for the metal object. So the heat absorbed is mass of the object, specific heat of the object times the temperature change. But I'm going to use his specific heat calculator, not the norm. Okay. Heat loss from the hot object equal sign mass of the hot object right here. C10 on the table 1 multiplied by specific heat capacity of the object on table 2. I'm going to use calculated value, then I have a little bit of error there, like in the fourth decimal level, and multiply by open bracket temperature difference. Okay, so it is heat loss, right? It should be a negative number. So we will calculate it that way. So which means T final minus T initial. So negative 3414.144. So you can keep like maybe 1 or 2 decimal places extra. That's okay. This is more than the significant figure we need. We'll keep 1 decimal place there. Then we'll take a look the heat absorbed by the water. Equal mass of the water, which is about 200 gram, multiplied by specific heat capacity of the water, 4.184. Multiplied by temperature different, T final minus T initial. That should be a positive number because it's absorbing. Again, I'm going to cut down maybe decimal places down to 1. It exactly positive and negative numbers. Instead of checking the PE, we'll check actually delta E, which means the energy change. So we should get 0, okay? So instead of PE, we'll check the delta E. This should be symbol delta. Symbol delta represent the change. Please change that into delta. And then we'll take a look what's the delta is. We know if our assumption is correct, the heat loss should be 0. So we will get exact that number here. Just we need to add these two numbers together, right? So just adding them, I should get 0. That totally perfect for this. But in-person classwork, we will not get that 0. That impossible. We will get some number, which means we are not doing anything wrong. Actually, there are places heat loss can happen. Okay, so I mentioned a couple of places. So not the rounding error or anything, just really the heat loss actually happening. All right, guys, question. And you need to add the functions like we done earlier. Both three functions here, Q lost for the metal one, then the Q absorb for the water, and change of energy delta E. All right, guys, question? Okay, then I can put you guys into a breakout rooms. Then you can try to complete all of the rest tree. So what you needed to do, the process is very similar, nothing different. For each of these case, you have to pick the right one which mentioning there. Okay, you need to reset the simulator first. And then for case B, we are doing the unknown metal number 2. Change this into solid first, then select the unknown metal number 2, continue. all the calculation in table 2 and 3, okay, for that metal too. And then we have unknown liquid also here. If you go into liquid, you can pick unknown liquid 1, unknown liquid 2. You can do that also. Same process, there's no difference at all. Calculation also very similar. You have to complete all of those. Okay, then after that we will take a look the latent heat part. Okay, so I will put you into the breakout rooms. Will take maybe like 15 minutes or so. That should be good enough, I think. Then I will bring you back. Then we will discuss the next part. Okay. Which formula? Last one. Right here. part, left-hand side corner. And then if you go all the way down, it will allow us to do the phase change, allow us to do phase change. Yeah, that's good now. Ice to ice H2. Uh, we can use like maybe 50 gram of ice, probably two much. We'll use maybe like 20, that should be good enough. Usually we'll use less than that. That allows 140. Temperature we can start at room temperature, something like 20 degrees C, and the water specific heat, and then we can view the graph and then start the experiment. Usually if we do an in-person class, we do it at least 2 times because there's a lot of error can happen. Because of that, we're going to take a look at the numbers and then we're going to take the average of 2 trials. Okay. I don't think anything going to change when we do it again with the simulation, but we will try again. Okay, we will do like 2 trials. Okay, that's it. Very simple. The water temperature increases. So the trial one, we can start mass of 8 grams. We have and the water is here actually because I need to include both temperatures for calculation. So we reach temperature, let me add 1 column temperature. I think I got it. All right. So the initial temperature of the water, room temperature about 20 in degrees C, and the final temperature is 7.52. Okay. You can use any, doesn't matter. I changed the initial temperature of the water into 20 C. That's how I started. If it is 31 when you're starting, you can leave it like that. That's okay. But make sure you use the right numbers, otherwise calculation will not give you the right answer, okay? So we started the ice at 0 degrees C. I started the maximum number of water, gram 140. Then my initial water temperature, I changes to 20. And the final water temperature was 7.52 because water losing energy, ice absorbing the energy, okay? If you have the different initial temperature for water, make sure you use that number. So that should be fine. That's it. Then let's calculate latent heat, usually per joule per kilogram. But since we're using everything in milligrams, we can keep the kilogram for the latent heat. So the equation, what we got earlier in terms of equation. So we put dice in. First, ice will melt because ice is in the solid state. So it will go with the liquid state. So then the ice will absorb because initially all of those are which is the energy from the CW minus CW times divided by 10 times the I. Now this part you can see if I do this way, this part going to stay as a negative number, but this whole part should become a positive, okay, this part. Because TF is actually less than now TI, so this whole part should become a positive. I can flip that. WCW TI minus TF minus MICWF, everything divided by MI. So that is LF. That's it. Now, simple, I can simplify this a little bit further. Then the calculation going easier. We'll take my here. Parenthesis TF minus TI minus CW times the TF. Okay. All right. Anybody have any problem with the sound or video? What is the problem? You can't hear anything? Not really sure what's going on. Nothing I can do actually. Yeah, probably the connection. Hopefully it will set it back in the right way. Uh, Nothing else can be done. Seems to be working from this side. So you don't hear probably we have the connection. Is there any problem that you from my side? Mm, still have the same problem? All right, guys. So we still have the same problem. Anybody? Most of you getting the bad connection? Okay, then let's continue. All right, so then let's continue. So our formula is, we take a look earlier. Let's do that here. We do it for the trial one, and then we'll retry again for another trial with a different initial mass or something, okay? All right, now what we do in this function, I need to write here. So equal sign, we can put parentheses, mass of the water. Maybe we need another parenthesis inside here. Mass of the water multiplied by specific heat capacity of the water 4.184 multiplied by parentheses temperature different of the water T final minus T initial. But if I get rid of the negative sign, it should be T initial minus T final if I get rid of the negative sign. Okay, so this should be T initial minus T final, because T initial is larger, 20 minus 7.52 close bracket once, and then divide by the mass of the ice, which I use 20, and then close brackets. Let's check how many brackets are there. I think there's one extra bracket here. Now it should be good. And then minus sign, parentheses, specific heat capacity of the water, 4.184 multiplied by T final, 7.52. And then hit enter. So I'm getting about 334.05. And let's cut down the decimals. We don't need that many. Maybe we'll keep one extra decimal place. The expected value is about like 340. That should be close enough. Okay, so we can compare those two at the end. Okay, all right, that's a plan. So it's working fine. So we have to recheck that with at least one more trial. Okay, so let's add that function here. This will be then L of F. We can say trial one. All right, so to do the trial two, what we can do, we can maybe select a different mass, otherwise it's not going to be much meaningful. We can pick maybe a different mass, reset the simulator. We'll put maybe, earlier I used the 20 gram of ice initially. Now we'll use maybe like little bit less. How about like something like close to 10? We'll use like about 10 gram of ice. Okay. No need to be necessarily 10. You can pick actually the number, any number you wish, doesn't matter, but make sure you use properly in the table. Okay. If I use 10 gram of ice, then I can do the same thing again. So that calculation, we can use the temperature of the ice 0 again. Then I can use the same formula. And the water doesn't matter technically. I'm going to use the maximum amount of water and the room temperature about 20 degrees C. Then my calculation is easy. And then that's it. It's very simple calculation. Only the mass of the ice I change. Everything else actually I keep in the same. Amount of mass of the water also changes. Initial temperature of the water also same. I just need the final temperature of the system. Now it should not go that further like it did earlier. Now it's only 12.32, right? That makes sense. I have less amount of ice. This part right here, again, it's the same function, but I have to retype the function because numbers actually changes. Click and drag might not work because here I have a downward direction. Here I have actually the rightward direction. So you may have to type the function again. Okay. So I'm gonna click and put here, and then I'm gonna edit this. So that is easier. So this part going to be then 54. This part going to be again 54. Part again. It may be easy to type the function completely from the beginning, I think. Not going to work if you click and drag, okay? Page 53. So this is going to be MW initial. Oh, this is actually editing everything. We'll write it down now. Equal sign parentheses mass of the water, new mass of the water multiplied by 4.184 multiplied by temperature difference. Now initial minus final, and then divide by mass of the ice, 10 grams, close brackets, minus open brackets, 4.184 multiplied by final temperature, 12.32, close brackets. About the same, because it's simulated result. If you do this amount of trial for this part of the lab is so important if you're doing this in-person class. Because of that, the water layer forming around the ice cubes are creating a lot of error. So that's why we do like at least 2 trials, and the numbers going to be like at least about like some difference we see generally. Then we take the average of that. Okay. I try to do exactly the same way we do in the class, but in the simulated result, it's going to be about the same. Nothing much difference. Then we'll take the average. That's it. It's very simple. You can use the average function on the Excel to do the average of these two. And then we'll compare that to the expected value. Okay. So this is going to be LF average. Okay. And then we'll compare that to the expected value, which is about 340. Equal open brackets ABS open brackets calculated average minus the expected value 340 close bracket divide by 340 close bracket multiply by 100. About 1% error. That because the expected value I just took it not exact value, the rounded value. That's why. So it should be fine about like 2% error compared to our in-person class error. This part we can get like 10% error very easily. Just so many parts adding up the errors when we do nothing we can do about it. All right, guys, any question? Don't need to make anything, don't need to do anything. Just this right here in G, you can add final temperature. That's it. You just need to type that and then type these numbers. That's it. It's that column is there. Borders, you can make the borders visible by using the font area right here. There's a black small like line box. If you click down arrow, you can create the all borders on. Then it will show all the lines. Okay. All right. So any question? Okay, so that looks fine. We can just take a look, couple of quick things. One quick things. Again, the amount of heat absorbed and the amount of heat lost by water. So that we can take a look. We probably will get the perfect answer because of the simulated result. But if not, we will see huge effect on this part of the lab actually. The units we can do joules for both, and again we are not doing PD for that. That checking right here at the end, we can compare them. We can do delta E. Okay, there's no meaning doing PD or anything. We'll do delta E like we done earlier. Here, make sure for delta E add the units joule too. That's important. We will get zero. I think we will get zero for this case. That's totally fine, but we will do it. All right, guys. So any question? Heat absorbed by the ice is actually that whole part, right? So the ice first has to melt and then it has to go into the final temperature. So equal sign, parentheses, mass of the ice for case 1, 20 gram multiply by, we'll use the calculated latent heat, okay, for the first phase change. That is actually 334. We'll use the average one. And then parentheses close plus open parentheses. And then the mass of the ice, again, I'm going to use the trial one, C53, multiply by specific heat of the water, 4.184, multiply by close bracket, final minus the initial. Technically, I just need the T final there, right? So that is, I'm working on case 1, that's going to be 7.52, close bracket. Then hit enter. Let's see what is there. Oh, I have extra bracket here, that's why. Okay, should be good. And get rid of all the decimals. We'll keep maybe one decimal place. That's going to be the heat loss. Sorry, heat absorbed by the ice. All right, then we'll take a look the heat loss from the water. So that's going to be equal sign mass of the water, case 1 I'm using. Do not mix those two up, okay? Trial 1 I'm using for that calculation. And specific heat of the water, 4.184, multiplied by open brackets, T final minus T initial. We'll do that way, then it should be a negative number, right? T final minus T initial. Then I will get it as a negative number because that is heat losing. So that's how we define the sign for those heat energy always in next two chapters too. When something lost heat relative to the initial state, it actually a negative amount of energy. When it absorbs relative to the initial state, heat is higher. So it's a positive number. Okay, it's going to be heat loss. Okay, so that's good. Then the difference of energy, just adding these two numbers. We will get like 0, that's okay, because it's simulated result. That's totally fine. But generally, we will not get 0 at all, okay? So we will get fairly good number here, particularly for this part, because the amount of error happening in real experiment is so considerably large. Okay, guys, any question? Okay, so looks good, I think. So all of these tables, when you copy paste, make sure you copy paste one by one to your report, okay, when you're doing the report. And the picture should go to procedure section. All the Excel functions should be included. You don't need to write like repetitively the same function. All the different function for each table must be included, okay. That's about it. We can take a look the last question. At least there's two questions I think we missed last time. We'll at least try to finish one of them because both of them are very similar as